In this video, we're going to look at solving rational inequalities. We have seen solving rational equations by clearing out that LCD. We've seen polynomial inequalities where we're finding critical points and using a sign chart. We're going to kind of put some of these concepts together for solving rational inequalities. The first step is going to be to set the inequality to 0, and then we're going to write it as a single fraction if necessary. To do that, we need to get a common denominator. Once we have a single fraction set to 0, whether it's greater than, less than, we're going to find our critical points. Now, if we think about our polynomial inequalities, our critical points were where the polynomial equals 0. For a rational expression, that rational expression equals 0 where the numerator equals 0. So that is our first set of critical points. They're the zeros of your numerator. But we also are going to include our restrictions, so the zeros of the denominator. So for a rational inequality, we're looking for two different types of critical points, a 0 of the numerator and a 0 of the denominator. When we're setting up our sign chart and we're marking those critical values, if you recall from polynomial inequalities, we either mark those critical values with an open circle or a filled-in circle. A filled-in circle was when we had an equal to inequality symbol, so an inclusive inequality, and an open circle was for an exclusive inequality, like strictly greater than or strictly less than. For the zeros of that rational expression, so the zeros of our numerator, we want to follow those same rules. So fill it in if it's inclusive, keep it open if it's exclusive. But because we're also looking at zeros of the denominator, those can never be included. We can't include a 0 or a restricted value in any solution set. So regardless of the inequality, whether it's inclusive or exclusive, any critical point that we get from the denominator must be marked with an open circle. Then we're going to test we're going to create a test point or find a test point in each of those intervals to determine whether the function is positive or negative. This is easier to do in the factored form, similar to what we had with polynomial inequalities. And then we're going to choose the intervals that make our inequality true. So really the only difference here is that now we're looking at critical points from two different places. All right, we've got the inequality x plus 2 over x minus 3 is greater than 0. Step 1 is already done. We have one inequality compared to 0, or one rational expression compared to 0. So now we're going to find our critical points. Our critical points are going to be the zeros of the numerator and the zeros of the denominator. So the 0 of my numerator is -2. The 0 of my denominator is +3. I always like to give myself an extra added identifier from those zeros of the denominator because we have to make sure we never include those. Now, because this is an exclusive inequality, it's strictly greater than, it's not going to be an issue, but it's always nice to have that habit in place to make sure that you don't incorrectly include a restricted value in your solution sets. So we have our critical points. We're going to mark those -2, +3. Both of those are going to be with an open circle. The 3 will always be because it was a restricted value. The -2 is not included because we're looking at an exclusive inequality. Choosing test points, we want to pick those easy values. So a value less than -2, we're going to plug x equals -3 in. Between -2 and 3, let's choose x equals 0. And greater than 3, we'll choose x equals 4. These are just samples, trying to pick some easy values. You could pick others if you wanted to. So starting with x equals -3, when you plug x equals -3 into the numerator, we get a negative. X equals -3 in the denominator, we get a negative. And the quotient, when you divide two negatives, is going to be positive. So those rules for multiplying and dividing positives and negatives are the same. Plugging in x equals 0, we get positive in the numerator, negative in the denominator. This is going to be negative. And plugging in x equals 4, we get positive in the numerator, positive in the denominator. And that ratio will be positive as well. We're looking for where this inequality is greater than 0, so that's going to be where it's positive. And that's going to be over the interval negative infinity to negative 2, union 3 to positive infinity. In our next example, example B, I'm going to modify this example slightly. I want to make it an inclusive inequality, so we're going to make this greater than or equal to 0. So this is already set to 0. It's already a single fraction. And now we want to find critical points. It's going to be easier to find our critical points if we factor this. It's also going to be easier to plug in our test points to determine the sign of the function. So we're going to factor the numerator, x squared minus 4, factors to x plus 2, x minus 2, divided by x minus 1. From here, the critical points from our numerator are negative 2 and positive 2, and from our denominator is positive 1. Again, I'm going to mark that positive 1 with an asterisk because I don't want to forget that it's a special point. I need to be careful not to include it. Setting up my sign chart, putting my critical points in order from least to greatest, so negative 2, 1, 2. Having 3 critical points gives me 5 separate intervals. Or I'm sorry, 4 separate intervals. 1, 2, 3, 4. The negative 2 we're going to include because we're looking for greater than or equal to, and that was a 0 from the numerator. So we're going to fill that circle in. 1 we're going to keep open because it's a restricted value. We're never going to include it. And 2, since this was a 0 of the numerator in an inclusive inequality, we're going to fill that in. Our test points, x equals negative 3, x equals 0, x equals 1.5, and x equals 3. And because we have that rational expression factored, now it's going to be a lot easier to determine signs. Plugging in x equals negative 3, our first factor is negative, our second factor is negative, our third factor is negative. And when we're multiplying or dividing, and when we've got 3 negative factors, that is going to yield a negative result. Plugging in x equals 0, our first factor is positive, our second factor is negative, our third factor, or the factor in the denominator, is negative. We've got an even number of negatives, so this is going to be positive. Substituting in 1.5, our first factor is positive, our second factor is negative, our third factor is positive. We have an odd number of negatives, so this answer is going to be negative. And then x equals 3, our first factor is positive, second factor is positive, third factor is positive, 3 positives is going to yield a positive. We're looking for where this inequality or where this rational expression is greater than or equal to 0, so that's our positives. So that's going to be from negative 2 to 1. And notice we're including negative 2. We are not including 1. Union 2 to positive infinity, where we are including 2. And one other comment that I didn't make when we were looking at polynomial inequalities or quadratic inequalities, oftentimes we do see this alternating pattern of signs. A lot of times we see that, but not always. Make sure you test a point in every single interval because sometimes those don't change sign. Okay, we don't have to necessarily change sign. So you want to make sure you're not assuming that alternating behavior and you are actually testing for the signs in each of those intervals. All right, now this last expression, that is a doozy. Now there is a slight typo in this one as well. The bracket here, and I'm not even going to try to read this just because it's such a complicated expression, should be paired with the bracket here. So that factor of x minus 3 is all the way out front. Now, this looks gnarly. This is not a pretty expression. We're going to see if we can make it look a little bit prettier. These are the types of problems that often cause students some anxiety looking at, but they're really not as bad as you might think it is by looking at it initially. So looking inside of the brackets, it looks like every single term here has an e to the x. So we're going to factor that e to the x out. So we have x minus 3, that's still hanging out in the front. I'm going to keep my pink brackets, but now I'm going to factor out that e to the x. And I'm going to use blue so we can see that we've pulled that out. So from that first term, we're going to be left with 2. From the second term, we're going to be left with 2x plus 1. And from the third term, we're going to be left with minus 2x plus 1, that entire quantity. This is all over x minus 3 squared, and we're setting this greater than or equal to 0. We can start simplifying a little bit more. One factor of x minus 3 in the numerator, or the factor of x minus 3 in the numerator, is going to simplify to 1 with one of the factors of x minus 3 in the denominator, so we're only going to have 1 left. Looking inside those brackets, and then further inside the parentheses, we've got a positive 2x plus 1 and a negative 2x plus 1, so those are going to sum to 0. So let's see what we have left in the numerator. We have 2 times e to the x in the numerator and x minus 3 in the denominator. So that very complicated expression now simplified down to something that looks way more manageable. All right, so let's find our critical points. Looking at the numerator, 2e to the x, e to the x, that exponential expression, is never going to be 0. Multiplying it by 2, never going to be 0. So there are no critical points from the numerator. Our only critical point is going to come from the denominator. And because it's in the denominator, we want to make sure we don't include that, even though we have an inclusive inequality. So our test points, let's plug in 0. Let's plug in x equals 4. Plugging in x equals 0. Our numerator is always going to be positive. E to the x is always positive, multiplied by 2, always positive. So we don't even really need to think about what that value of our test point is going to do because the numerator is always 0. Plugging in 0 in the denominator, that's negative. So this part of the function is going to be negative. Plugging in x equals 4, again, the numerator is always positive. And if I plug 4 into my denominator, that's positive, resulting in positive. We want to know where this rational expression is greater than or equal to 0. It's going to be in the interval 3 to positive infinity. And again, because 3 was a restriction from the denominator, not included in this interval.